thanks for having me and for the introduction. Great to see a lot of familiar faces on the call today. I trust you can see my screen now. Let's see, Rubin Hall. I'll sort of frame this all up for you folks who might not be in the New York area. It's for New York University, Rubin Hall Retrofit. It's a building that was constructed in the 1920s, originally as a hotel, and it's a student residence. And this project is a renovation of it to continue to be a student residence, but also with very high energy efficiency and sustainability goals. So first, a little bit about NYU for you folks who might not be familiar with it. NYU, one of the largest institutions, global institution based in Greenwich Village in New York City. They have 15 sites globally, 24,000 employees, 60,000 students. And in New York City, they have a significant presence with 200 buildings, 15 million square feet of space, almost 2,000 utility accounts that they keep track of. And they represent 0.3% of New York City emissions, which is, significant, and they can move the needle in terms of what they do and what example they set for the rest of the city and other institutions. So in 2007, they adopted a climate action plan to reduce greenhouse gas emissions from buildings by 30% in 10 years. They actually achieved that early, within 5 years, and then reset those goals to carbon neutrality in 2040. So they've had real realization of their climate action plan, and they continue to push that not only in their buildings, but in their operations as a whole. And what they find is that there's a lot of different reasons to pursue climate-friendly buildings, but one of them is certainly just that they're healthier buildings, healthier for their students, healthier for their employees, create better working environments, learning environments, and living environments. So, a lot of different reasons to pursue high sustainability goals, and beyond just energy efficiency. Some of their recent journey on increased performance buildings include Brittany Hall, which was constructed, or which was very similar to Rubin Hall. It was the renovation of a 1920s building that was originally constructed as a hotel used for student residences, I believe since the 1960s. And they did a renovation of that 2013, 2014. And with that, they insulated the exterior envelope, installed all new mechanical systems, added air conditioning. But it was with systems that included a boiler, cooling tower on the roof. And they saw real energy savings with that, and improved thermal comfort and improved space for the students. Students are able to control the temperatures of their room compared to the steam radiators that were there before. And they installed double pane windows, which are sort of standard for that time, that also create a better just environment for the students amid a noisy New York City environment. So Brittany Hall was a great progress from what the building was, but today we're talking about Rubin Hall. Some time has progressed since the Brittany project, and we started at FXCollaborative. We started working with NYU in 2018, looking at Rubin Hall and a number of different residence halls from different time periods. And what's sort of the future of these buildings within the context of their climate action plan, within the context of New York City in terms of Local Law 97, which starts to impose fines for carbon emissions, and within the context of Con Ed and other utilities starting to not provide new gas hookups, and using the passive house framework as a way to explore the future of these buildings. So we did this energy master plan with NYU, identified sort of different pathways for the future of each one of these buildings, including Rubin Hall. And then in 2021 started actually implementing the design of that. And what we end up with, that I'll go through in detail today, is all electric systems with triple glazed windows, dedicated outdoor air supply in the building, high resiliency result of those systems and that improved envelope, passive house certification, which right now we're on track to be the largest passive house EnerPHit certified residential building in the world, as long as nobody beats us to construction. And NYU has gotten great support from NYSERDA, from New York State, from Con Ed, the local utility, for the efforts in terms of energy efficiency. So a little bit more about Rubin specifically. It's on 10th Street and 5th Avenue. So you folks who are familiar with New York City, lower 5th Avenue is part of the Greenwich Village Historic District, very New York environment. This building from 1920s is a very typical of classic New York, an important part of the fabric of the city. And by being in the historic district, New York City Landmarks Preservation Commission has jurisdiction over and say over everything that happens on the exterior of the building, in terms of adding equipment on the roof, changing windows, anything like that. They have say over, and really preserving what's there. And you can see, from the photo here that it's already a well-preserved building and very characteristic of the architecture of the area. So that presented a number of unique challenges, whereas a building elsewhere in the city might have allowed for other solutions, such as overcladding or otherwise. So NYU, they look at, we looked at with them, the sort of building or project as a standard business as usual renovation, and then in the early phase of this, looking at different energy conservation measures and arriving at the sort of set that we established here with the passive house framework. And what they find is that sure, there's initial additional costs, and a lot of that was due to the fresh air supply system that I'll go to in more detail. But there's reduced cost in terms of energy over time, and then avoiding those fines over local law 97 that will be imposed in the future. And then there's, beyond just the sort of financial aspect of it, there's the increased health and comfort and other aspects of just improved buildings that I mentioned before. This, Rubin Hall will be a more comfortable place for the students. They'll have high performance windows. They'll be able to sleep better at night, be fresher for their classes, and get more out of their education at NYU. So there's a lot beyond just the sort of business the financial aspects that NYU views this through. So now I'll get into some of the details, starting with the exterior envelope and sort of framing that up. You see the existing building on the left, and are sort of pulling apart the different percentages of exterior enclosure. What we see is the windows are 20% of the exterior envelope. The solid portions, the walls, the columns, are about 66%. And then the slab that intersects that wall is about 14%. Each one of those presented their own challenges and opportunities for energy improvement. First, I'll go into the windows. The windows were a significant undertaking of this project. We sort of knew that from the beginning, but we only fully appreciated that once we got into the details. The photo on the left, we were very fortunate to have this from 1926, just shortly after the building was originally constructed. Very high resolution photo that we were able to zoom in and see all the details of. And then the building on the right, as it stands today. Again, you can see it's, most of the historic fabric is still intact. The windows, however, were replaced in the 1960s when NYU purchased the building, converted from the hotel to the student residence. And they, at that time, they removed the wood historic windows, replaced them with single pane steel casement windows that now, years later are at the end of their useful life. And those steel casement windows, did not resemble the historic windows in any significant way. And windows in general are really a defining feature of a historic building, and Landmarks Preservation Commission, wants to make sure that they're done correctly. So when we started thinking about them, we realized there's a lot of different criteria that comes into play in terms of how we design the replacement windows. And I'll go through that on these following pages. Starting with historic appropriateness. And what's in red here are sort of strict guidelines coming from regulatory requirements or energy requirements. The other ones are sort of a little bit optional. But the original windows were double hung windows. So ideally, Landmarks would see those double hung windows continued in that same operation. And the original windows were wood. So that, became part of the discussion as well. The configuration of the windows, again, those double hung windows, they were typically divided lights above and larger panes on the bottom. But those double hung windows have a offset of the glazing from the top sash to the bottom sash, which is really a defining feature of the building. The dimensions of that crossbar and continuing on to the details of the trim and the rest of the windows were very important, and a lot of conversation around that. Landmarks preservation also has say over the glazing area. So ideally, we're matching or coming very close to the original area of glazing of the original windows, although they do have some more flexibility for high performance windows where you're allowed to reduce that area by a little bit more. And then consistency, once you replace windows in a portion of the building, really have to replace them across the whole building so it's a uniform look. So then on to performance. In terms of reaching the passive house level of performance, avoiding those local law 97 fines, we realized that air infiltration is really a key factor in that. And you cannot meet high air infiltration goals with sliding double hung windows, and we had to go with some different options on that. And then thermal performance meant thermally broken frames and triple glazing. In terms of material and durability, Rubin Hall is 17 stories tall. One can't repaint wood windows every few years and need to erect scaffolding to do that. So that started to steer us towards aluminum framed windows that were more durable and also met the performance requirements of a high-rise building. Continuing on, accessibility was a key factor as well. Meeting ADA requirements was very important. And that dictated things such as the force on the handle to open the window and the location of that handle, so it was in reach range so anybody could use them. Onto maintenance and operations. This was all sort of complicated by these windows actually being very large, 6 feet by 6 feet, which doesn't necessarily show up in that, you don't realize it in that photo, but those are large windows to be double hung windows and presented a unique set of challenges as well. Maintenance and operations wise, being able to clean them from the inside is important. Being able to have minimal rain come in when students leave their windows open, go to class and it's pouring rain outside, and then having insect screens that are removable. So this was sort of the set of criteria that we had to design around. We had to explain this not only to ourselves and discover it for ourselves, but also explain to NYU, but even more importantly, explain this to Landmarks Preservation Commission what is our decision tree in terms of what the design criteria for these windows should be. So we generated a few of these sort of flow charts that explained that all and just explained how some of the sort of typical configurations were not possible or otherwise problematic. What we arrived at was, I guess we sort of brainstormed as a team, what are all the different ways windows can open and be cleaned? And we ran through many different scenarios, only a few of which are presented here. And what we sort of first looked at, or one of the options we looked at, was this hopper lower. The bottom portion of the window would swing in. When we got into the details of that, we realized that, again, these large windows, that bottom sash would be 3 feet by 6 feet, triple glazed, that was very heavy. And you could not get hardware that worked with that, or you could not, physically move that within the ADA parameters of force requirements. So we moved on to a casement lower. Maybe the whole bottom sash could swing in sideways. Again, ran into trouble. 6 feet wide cantilever of triple glaze sash was just too heavy and not achievable because of that. Then we said, well, maybe the bottom sash could swing in an awning action. And we found that, well, sure, you could clean that, but you really could not reach around and clean the top sash. The water infiltration when the window was open was the key, and that was discounted. Then we moved into, well, maybe the bottom sash could swing out. That presented some difficulties in terms of landmarks. They prefer that the window not swing out and sort of change the geometry of the building when they're open, but also presented issues in terms of one could not clean the outside of the window. So those were a few scenarios that we looked at. And then we sort of finalized around these three, working really mainly with Wausau and Schuco, both working with their engineering departments and really getting into the details of exactly what hardware and what the possibilities were. So on the left side of the screen from Wausau, we said, well, maybe that outswing awning could work. Issues of the cleanability, but even more important, we discovered once we started to add some of this functionality and hardware, the performance of the whole assembly went down and was not meeting the energy goals that we were looking for. So we moved on, well, okay, if this isn't cleanable, maybe we could create some sort of hybrid of the top sash going in, the bottom sash going out. That also had those energy implications, but also each one of these adding hardware started to thicken up the frames, make them look less historic, and everything sort of got chunkier. So we also worked with Schuco. Schuco was in development of a sort of historic recreation window that was a single sash. The entire opening would tilt in for ventilation and also be able to turn for maintenance. They had been developing a product based on double glazing. We worked with them to adapt that product to triple glazing. And we found that that met as many of those boxes, checked as many of those boxes that I mentioned as possible by having that full sash tilt in. We were able to minimize some of the framing, get a great performance from it, and get pretty close to the historic look. So, we did all this design work. We worked with NYU, worked with this manufacturer, but getting this through landmarks was a process. And we had two public hearings, actually public hearing and public meeting, where we laid this all out for them, worked with staff in preparation for those meetings, and explained this as our sort of ultimate solution. Going back to the 1960s replacement project, we were fortunate to have this drawing from that window replacement set, so that that became the basis between this drawing and those high-resolution photographs in terms of what the historic window was that we were starting with. This is the window that we came up with, which you can see is pretty close. We were able to minimize that that meeting rail. While it is a little bit wider than the original, it's still largely the same. And we went to that first public hearing. And what in New York City, landmarks has seen passive house windows, but more typically on the sort of townhouse Brooklyn brownstone scale, which a wood window is appropriate for that, but not for our application. So this was sort of a new thing to explain to them and get everyone's buy-in on. At that first public hearing, we were told that our proposal was a little bit flat and they wanted some more articulation of the window and the framing. And we ended up adding on the trim that's indicated in yellow, which further pushes out that top sash look to get a little bit more depth, a little bit more shadow. And you can see also, in this section, the offset of that top glazing versus the bottom glazing. Even though the whole window is operating as one, we have that geometry offset. So we're, closely mimicking the original window configuration. So let's see. And then this is where we arrived at. The original windows on the left, or the existing windows on the right, those casement windows, and then the final design with our proposed windows, also in a color that that was close to the original. So you can see we're largely restoring that historic fabric with the new design. Now on to the exterior wall. I think that was about the 66% of the envelope. And I'll start with this floor plan because what it demonstrates is that the building as it exists today and the configuration of the interior largely remained as is in the renovation. It's a tightly packed building. It's New York City and every square foot counts, and we needed to fit as many students and as many beds as was practical in this. And this is important because the exterior wall, as it became thicker, started to decrease that bed count. So there was this sort of intersection of numbers of beds, finances, and costs to the students and thermal performance. And then this is an example of sort of a bird's eye view of one of the rooms. Many of these rooms are triples. There's 3 students, 3 beds, 3 desks in each one of these rooms. So every inch counted and impacted what we could do on the exterior envelope in terms of thickening it up. During one of the summers, we were able to get into a few of the rooms and do some exploratory probes and mock-ups. And while, in theory, this building was brick on hollow terracotta block with plaster applied to the interior, over the 100-year lifespan of this building, that construction sort of evolved as things were repaired and replaced. And while that might have been the majority of the assembly, we found that there was gypsum board and other products sort of patched in as the building was maintained. And also we learned that the floor slab was concrete slab with this sort of loose cinder fill, which is characteristics of buildings of this age. And I think we can all agree that the existing construction did not really look like anything that was high performance from an air infiltration point of view, and presented, some challenges in terms of how to deal with all this. So the exterior wall is where a lot of different things come together. You can see the windows that are obviously in there, and we supported those sort of independent of the existing wall assembly because that was sort of too much of an unknown with those hollow terracotta blocks. To manage all the unknowns in the exterior wall, we applied a gypsum board sheathing to the interior face of that to act as the air infiltration barrier, with all the seams taped and joints to adjacent surfaces taped. Added a continuous layer of spray foam insulation and then spray foam insulation in between the studs as well. And that was all open cell with, believe, a waterborne agent and low global warming potential of the open cell insulation as we could get. And we looked at mineral wool, but that would have increased this whole assembly and started to decrease the bed count. So that's how we arrived at that assembly. Then interior to the studs, we have a variable permanence vapor barrier, and then gypsum board to the interior of that. Underneath the windows, we have the fan coil units, and then we have the risers for the fan coil units also up against the exterior wall. This is a zoom in of that same assembly showing, some of that taping to all of the adjacent surfaces. We had to pour in a little bit of a new concrete slab to get a good surface for that, and all of the various layers adding up on the exterior wall. Here's some of the details as well with that same window detail, and looking at that slab that we poured in, that little bit of finished floor we had to build back, filling in where wood baseboard was, adding the sheathing, taping all those seams continuous to the floor, continuous to the window, and onto the ceiling. We worked with our exterior envelope consultant and took a few brick samples from the existing building to understand their performance, their porosity, to help us decide, how much insulation to add, what insulation type that was, whether it's closed cell or open cell. And we found a variety of bricks across the building, and thus went with the open cell that was sort of the safer choice in terms of managing the moisture in the building and not changing that dynamic too significantly from what the building had experienced over the previous 100 years. Onto the mechanical systems, all electric, as well as I previously mentioned. Fresh air distribution and high performance energy recovery units, dedicated outdoor air supply on the top of the building, threading those services down through the existing structure, which I'll show on the coming slides here in terms of some of the challenges presented with that. Heating and cooling all provided by heat pumps on the roof going to fan coils in each room, and domestic hot water fed from those same heat pumps on the roof going to water-to-water heat pumps in the cellar for domestic hot water, and feeding to a high zone and a low zone in the building. Bring that floor plan back again, reminding us all of how dense this building is. And there was no air conditioning in Rubin before, so there was not significant shaft space available. There were, though, these shafts indicated in orange, which were used for plumbing and for a little bit of exhaust from the restrooms. And we worked closely with our mechanical engineer to locate the supply ducts and the exhaust ducts in those shafts with the plumbing, some tight Swiss watch work there to get that all to fit in. But we're able to introduce these new modern systems, ductwork, without creating any new shafts. And that was significant in terms of a cost savings and not having to do new structure, not having to do new slab openings. And then in terms of a space savings as well, not impacting that bed count in any significant way. And then the water side again was located next to the fan coil units adjacent to the exterior wall. Those systems were all fed with equipment on the rooftop, and you can see this bird's eye view. While the rooftop is not architecturally significant on Rubin, it is complicated. There's this setback penthouse, there's various bulkheads, there's a water tower on top, and this presented a number of challenges in terms of just physically being able to fit the equipment in and locate it in a way that could tap into those existing shafts, work structurally, work from a noise code perspective, and work from a architectural and historic perspective in terms of not changing the roof in a significant way. To give you a feeling for it, this is the existing roof plan as the building is today, and there's very minimal equipment on it, some exhaust fans and domestic water tank. And then in our new design, significantly more equipment to supply all of those systems, with the energy recovery units, dedicated outdoor air supply, largely located on that penthouse roof and feeding into existing shafts. The heat pumps we had to strategically push to the back of the building so they were less visible from the street, but also presented some challenges in terms of meeting noise code and being the adjacency to neighbors. And then locating an emergency generator within that former domestic water tank house so that students could shelter in place almost really indefinitely should there be a Hurricane Sandy or similar event in the future. So all of this required careful coordination with all of our engineering team. Another thing to add into this, there was a zoning regulation to screen off much of this equipment from the neighbors as well. So to explain this all to Landmarks Preservation Commission, we presented those plans, but also did a real world mock-up of scaffolding, demonstrating the mass of those pieces of equipment and the screen wall, and demonstrated that while maybe portions are visible from the public way, they're not significantly visible and don't change the historic characteristic of the building in a significant way. So I mentioned sort of resiliency. We're adding this generator that did not exist before, and we wondered, well, how can we have students stay here in even in extreme temperatures if we were to size that generator to power all of those heat pumps that would become untenable in a giant generator. And what we found was we could put the DOAS, dedicated outdoor air supply units, on that generator, combine that with the highly insulated exterior envelope. We could sort of moderate the temperatures even in extreme conditions. And throughout the year, even in the middle of summer, middle of winter, I think we were always between the mid 65 and 90 degrees or so, and avoiding sort of those extremes so students could remain in the building sort of indefinitely. So existing building, there's a embodied carbon story here. Certainly, we're retaining a lot of stuff, right? We're not building new foundations. We have this structure, we have this facade that we're all retaining. And some rough calculations indicate sort of 94% of the existing embodied carbon will be preserved because we're sort of surgically doing this renovation. What we did have to focus on, though, sort of the hot spots were the insulation, gypsum board, and flooring. And we tried to choose all those products strategically from a carbon perspective and an indoor health perspective to be as responsible as possible within those parameters that were sort of available to us, like as discussed in terms of the insulation on the exterior. So there's a lot of lessons learned with this, far more than 6, but kind of framing them up. Doing that feasibility study far in advance was really key. It gave NYU an understanding in terms of what the options were, what the potential cost is, where what requires more analysis in the future. So doing that far in advance was key, and then starting early, making sure that energy goals are understood right from the start of the project, right at the kickoff. Sweating the details. While that early energy study said, like, sure, let's do triple pane windows, it wasn't until we got into those details, talked with manufacturers, got their engineering department to look at the handle and the force of the handle of the actual hinge that was available, that we really uncovered what the real issues are. Between LEED and Passive House, those third-party certifications were key in terms of rallying people around those and saying this is immovable criteria. LEED required that dedicated outdoor air supply, that mechanical ventilation. And that was at a significant cost and technical complexity to the project. But as the team reminded itself that LEED is sort of the baseline needs to be met, that DOAS system sort of had to remain in the project as the project evolved and prices were looked at. Blower door tests. We have yet to do a full building blower door test. That's something that we would like to do before construction. Unfortunately, Rubin Hall is occupied really year-round, 24 hours a day, 7 days a week, and we were never able to have the building be vacant or empty of student belongings, that NYU is comfortable in terms of having that blower door test. So we're going to do it immediately before construction this May of 2023, and create that baseline. And then over the past 2 years, certainly projects, everything has seen volatile costs, volatile lead times. I think each time we spoke with a window manufacturer, the price of aluminum on the commodities market had gone up 30%. Things like mechanical equipment were also volatile, and also sort of backed us into, gave us limited options. Some mechanical equipment, some generator manufacturers, some heat pump manufacturers had 100-week lead times. That's just not practical within the time frame of this project. So selections were sometimes limited and changed as the design progressed. So obviously, I did not do this project by myself. A lot of people to thank in this, and a lot of folks beyond FXCollaborative. Obviously, NYU for having the vision to do this project, having their climate action plan, and remaining, on keeping the team on track in terms of what the goals are. I think on the call today, my colleagues Elizabeth Himmel and Jenna Rimkus were key in figuring out all the details of this. AKF group were our mechanical engineers. Stephen Winter was our passive house consultant. SGH was our exterior envelope consultant. Silman Structural Engineers and Building Conservation Associates were our historic preservation consultants. And with that, Rubin Hall is being lined up for the next 100 years, and hopefully sets a vision of what the future of all these existing buildings can be. It's typical of, millions of square feet in New York City of pre-war housing, and everyone's sort of wondering, well, what's the future of energy in these buildings? And hopefully this sets an example for others to leapfrog behind us in terms of energy efficiency and inventiveness. And it's gotten the conversation, increased the conversation within landmarks, and we hope you all take what we learned on this project and continue to push your projects well beyond this. And I think that's it for me.
Thank you so much, Michael, for that presentation. You've been getting a lot of compliments on the chat about how clear the graphics are, and just a really well done presentation. So thank you very much for sharing.
Great, thank you.
So first, there was a lot of interest from everyone about the wall assembly in general. First was Harvey's comment about looking forward to hearing about the wall assembly and the air barrier implementation. Harvey, did you have any question related to that, if he's still here?
Yeah, thanks. Great presentation, and really the wall assembly photo, and I know Shannon had mentioned it, was just fabulous. My question was, after seeing your original photos when you were taking the wall down for the demo, one of my main concerns was just the water infiltration, and then I'm wondering what your air barrier was. And I think you said something, you put some gypsum board and they were taped as your air barrier. Were you concerned with water infiltration from the exterior into the interior, given that the brick looked like it was really, really porous and not in good shape? And thank you again.
So the building is also going through a exterior restoration process. So it's going to be repointed where needed. Some, cracked bricks and other assembly will be repaired and replaced. So we're not necessarily too concerned about that. And that sheathing that we are applying is a glass-faced gypsum board sheathing, like a dense glass gold kind of equivalent. I think though it's fairly thin, 1/4 inch thick, but the brick should be really holding the bulk of the water out, and it's more of the sort of moisture that we're managing, and that WUFI analysis that we did showed that was not going to be too much of an issue. it's sort of more like the terracotta, that plaster on the interior surface that's not providing the water barrier, that was a little bit more of the crumbling sort of condition.
Great, thank you so much.
Great, thank you for that question. Next up, we have John Wolfling. Would you like to unmute and go ahead and ask your question?
Yeah. Michael, you mentioned, and first of all, thank you for this good presentation. I mean, it was there, as you pointed out, there is so much square footage that's like this in New York City that if we don't come up with a model to address this, we're not really going to be able to move the needle on our city's energy consumption. So this is great to have this shared with this group. You mentioned doing a baseline blower door test, which hopefully you can get some results from that, and it just doesn't leak out everywhere.
Right.
So you might have infinity as your baseline, but is there also a baseline on the EUI, either site or source? And I have a follow-up to that, which is at 39, is it the density of the occupancy and the plug loads and all the, what's driving that 39? Or is it some sort of limitation related to the existing building, like the slab edges and not being able to address those thermal bridges?
I mean, there's probably a few things behind that, though. You brought up kind of the two key things, right? As we drove down the energy usage of, the heating system, the cooling system, domestic hot water, plug loads became like the thing. And much of that was like IT loads and like the IT switches and the cooling required for the IT switches. We had lots of discussion with the IT designer in terms of, do you really need all of those cables for all of those students who might just be using Wi-Fi or whatever else? And I think that's the next thing to sort of push on, and especially through COVID and Zoom, and you could have 600 students on Zoom and gaming and everything else simultaneously in the building, that everyone's sort of concerned about that. So plug loads were significant. And then you brought up the slab edge. I was personally like shocked when we were doing that analysis of, well, like how much that uninsulated slab edge decreases that overall assembly. And I think we had a insulated assembly of our 20 total. I forget what the overall average ended up being, but those zero insulated slab edge are just such sucks of energy out of the building that you just can't do anything about in a landmarked building, right? If it was,
and it's 14% of the envelope, if I remember correctly.
Yeah, when we did that, like really 14%, like, but 8 inches or whatever its thickness is, adds up, right? 8 inches out of an 8-foot tall ceiling, so that was surprising, and it is definitely a limitation, and points to overcladding. Is like the way to change that, but not for this type of building and not without significant cost, right?
Okay, great, thank you.
And I'm like scouring my notes here for the existing EUI. I don't know if I'll be able to come up with it.
It was 63 based on LEED.
There you go, Jenna, thank you.
63, sorry.
And was that 63 existing, or was that 63 baseline LEED model?
It's baseline LEED model.
So existing was higher than that.
Yes.
Yeah. If anyone really wants to geek out on these details, Cecil Scheib from NYU, who is really the champion of all things sustainability on this project and beyond, myself and other members of the design team, we wrote a paper for the ACEEE, American Council on Energy Efficiency Economy, that you can geek out on, 12 pages of facts and figures and numbers, and look that up. That's available online.
Oh, that's amazing, Michael. Thank you for letting us know. I'm sure there are a lot of people here today that will definitely check that out. These are really great questions, very detailed. Next, we have Shannon Pendleton. Would you like to ask your question?
Sure. Hi, Michael and FX and team. Amazing. I think you need to rebrand. Really great presentation. I came a little late, so I look forward to going back to the recording, but I entered when you were iterating on the windows and particularly the functions, which I thought was really thoughtful and clear. Did you consider battering the jambs at all to increase the amount of light, or were insulation or cost prohibitive for doing that, or was it just not?
In terms of like sloping out the jambs on the interior,
Yeah.
I think from a insulation point of view, that's challenging. But yeah, that was sort of one of those things we discovered, that those windows are pretty far inset into that very thick wall now, and actually presents a whole nother set of challenges in terms of how to like take off the custodial limit lock
Yeah.
on those windows. I forget what our total wall thickness was, but it's, you know, between the brick and the terracotta and then all of our insulation, it's significant. But I don't think we could have sloped those in a significant way.
Thanks.
Thank you for that. Jane, hi Jane. If you'd like to speak up and ask your question. You're up
Hi,
next.
thanks so much. Fantastic project and really a model for New York City. I have two questions. One is the light and air requirements for New York City on the windows. If they're locked, I assume the turn function is locked except for cleaning, so they can only tilt for ventilation. Was that an issue in providing 5% window area for ventilation? 5% of floor area?
Yeah. So I could go even more into the operation of the windows. So yes, they typically, you know, tilt in. I think in our typical windows, those were fine. There's also sort of an annex building to the east that has a different window configuration that we, you know, we're a little bit closer in terms of the legal light and air, but we were able to make it work. Those windows also, you know, turn not only for a custodial function and cleaning function, but some of the rooms that are dedicated accessible rooms work as a you know, casement window all the time, and then some of the other windows are convertible for that use as well.
And then I had another question about the wall assembly. I understand you said the choice of spray foam versus mineral wool was because of the thickness, but does open cell spray foam is not as high in R value as closed cell, right? And then you had to choose open cell spray foam so that the wall could dry in both directions. Was that the reason? And did that allow you to not have a smart vapor retarder on the inside? Like, is it permeable enough to dry, but still impermeable enough that you don't get the warm moist air getting to the cold surface?
Yeah, so we have, go ahead.
Yeah, we do have the smart vapor barrier on the
Oh,
interior.
you do? That's what I was
Yes,
wondering. So you
yes.
also have that. Okay.
Right,
What
that's
what product did you use for that?
Oh, keep talking. I'll look it up.
Okay.
I don't have it off the top of my head.
But yeah, that was like part of the process and design of, we did the analysis and we said, oh, well, like, there's just so many unknowns. Maybe closed cell like isn't the smartest choice, and open cell, can we like tolerate that extra, you know, thickness of assembly? And kind of scoured the building again. Okay, like, yes, we could make that little bit of extra thickness work and still fit all those beds in there. I think, you know, another inch of
Right.
mineral wool might have tipped it over the edge.
Yeah, because the mineral wool, I mean, I like the fireproofing of it, and also if the building has a leak that you can pull it out and put it back more easily, so that I generally favor that. But I was just curious, the other advantages to the spray foam, which I kind of understand. So
Yeah.
All right, great, thank you.
You know, and all the kind of that product and all the interior products as well. You know, I'll give a shout out also to Jace Kwan in our office and our sustainability group. And also Dan Pacelli, our Director of Sustainability, has been key on this project and you know, in helping us review all those materials, achieving all the goals of this project as well. So just want to give a shout out to them as well.
We
I
are,
just want to say for this group that this is an incredible example of a project where there's like, you know, some sustainability people kind of just giving the team a nudge, and the team ran with it and just knocked it out of the park. So, you know, I know that we all talk about in Passive House Accelerator and your Passive House and everywhere else that, you know, this is exactly the kind of thing that we all want to happen to scale it all up.
Yeah, Dan keeps us all on track across the office. Hey, did you think about this? You know, are you doing this? Here's a good opportunity here. So yeah, that's required to have someone that's like a little bit outside of the project, who's not in the details to keep things on track.
That's a really great point, and thanks Dan for joining. It goes to show that it takes a team in the office, not just the you know, above and beyond the Passive House consultant, because you also have Stephen Winters doing the WFI model. Is that correct?
We had, I guess the WFI model was for the exterior envelope was SGH.
Okay.
Exterior envelope consultant. Stephen Winter did the Passive House energy model, and AKF did the sort of iterative process of sort of their energy model, looking at the different systems.
Wow. And Jenna or Gina?
Jenna.
Jenna, you were going to say something as well.
Oh, the membrane. Cheryl is from SGH is actually on certainty membrane.
Great, thank you.
Great, thank you for that. So Harvey was next on our list, but I think he asked this question earlier at the beginning of this session, and it looks like Mackenzie is up next. Do we still have Mackenzie with us? Mackenzie Stickney, if you're there, you can unmute. I think you're muted, actually. I can't hear her. So I'm going to ask her a question. She says, it looks like steel channel framing was used for the walls. Is that for fire performance? And did it greatly affect thermal bridging?
So, you know, we framed out those new interior walls along the exterior with steel studs, sort of typical wall construction. We held that back from the existing wall assembly, so there was a few inches of continuous insulation and then the spray insulation in between the studs as well. And then I kind of mentioned it, we also use like doubled up studs on each one of those windows on the side with plates to sort of cantilever out and capture the windows. We were afraid with that hollow terracotta block that we would not be able to support the windows in that, or that in the limited you know, construction schedule, that like there will become all sorts of unknowns and we'd have to come up with alternate designs. And we said, well, let's take that unknown of the support of the windows with the terracotta out of the equation. Let's just support it independently, and that's why we went with that option.
And were those metal as well? The
plates,
plates.
I believe they were steel, right?
Yes.
Yeah.
But they're intermediate though, so they don't affect the thermal bridging as much.
Yeah, they're just local.
And
They're local.
They're not right. They're not accounted in the modeling.
And then your insulation on the inside kind of meets the window at the edges.
Right.
And
yes.
Yeah, that makes sense.
I think I saw, and I just kind of mentioned now, I saw a question about schedule. So construction is starting this spring, you know, right after graduation in May, and the building will be completely, you know, empty of students until the following August, when on move-in day, all 700 students need to move in. So yeah, it's a very defined schedule that has to be met.
Great, thank you. So up next, we have Pam Stuckey, if I'm saying that right. Would you like to?
Yeah, that's great. Thank you. What a wonderful presentation. I didn't know if you ever run into, because I'm in Nevada, and we always run into electrical capacity when we try to do or add new things around here a little bit. Does that ever become an issue with the new equipment and the electrical capacity in that street, that region, et cetera?
Available electrical capacity in the street, that was not an issue. And I think what we hear in New York is, that infrastructure is really sized for the summer peak, which this building, I think it consumes more energy in the winter with the heat pumps. So there's nobody else is running. There's not as much, tax on the electrical grid in the winter. So there's sufficient capacity for this. So the building is getting upgraded electrical service from Con Ed utility, but that's available, and Con Ed have been partners on this, and they're funding, they're giving some funds for the project, and would have made it happen because that's their goal, to reduce their natural gas infrastructure.
Okay. Thank you.
Great. So, and next up we have Shane Pollan. Are you still here?
I am, thank you. First of all, wonderful presentation, and even more importantly, great work to solve these issues. My question is, with the exterior wall and the movement of the insulation inside, as you resist the movement of what you've described as a building that's almost always occupied, and you resist that heat from getting to your brick, is there a concern that the brick will be colder than it's ever experienced, and how that brick might respond to that cold temperature from rain, et cetera?
There was definitely that concern, and that was what that WUFI model helped us explore that concern and look at our assembly, look at the brick, and look at those unknowns of the brick too, right? We thought it was kind of one brick, but we realized it might be a whole variety of bricks. So that all guided our assembly, drove us towards that open cell insulation, and we were all comfortable with with how much that envelope would, how different that brick would be from what it has been over the past 100 years, and that we were not doing anything negatively to impact that. But the WUFI model was required to prove that out, and the samples of the brick from the existing building were instrumental in proving that out.
And when you say samples, so you took samples and those were tested to see the permeability of the brick.
Yeah, SGH took those to their lab and tested permeability.
Got it.
And found this wide variety. So we said, okay, we're going to go with the worst one because you don't know exactly what might be there.
That makes sense.
Thank you.
Great question, Shane. Next up, we have Andrew Peel. Go ahead, Andrew.
Can you hear me?
Yep.
Okay, great. Yeah, I'll echo the sentiments of a great presentation and project.
Thank you.
I have a couple on the mechanical side. So I was wondering if you considered wall or ceiling mounted fan coil units instead of the floor mounted to increase usable floor area. And the second question, I love the resiliency investigation of if power goes off, what's the temperature going to be like? How do you deal with the sizing of the generator? Did you consider adding a bit of supplier cooling to the ERVs to, not for full building cooling, but just kind of take the edge off like some of the ventilation load and humidity so that, you could maintain somewhat more comfortable temperatures?
Yeah, so that's what we did. Those ERVs, those DOAS units are on the generator and, temper temper the space and keep it in that 65 to 90 degree.
But you don't have any active, even just a bit of active cooling capacity on the supplier. Just it's just
there's the DOAS units have a VRF component that's tempering that air. That's, I forget exactly what it supplies it at, 70 degrees or something like that. So
okay, right.
So then your other question was about like the location of the fan coil units. You know, when we originally like conceived this, we said, oh, you know, should those be in the ceiling, you know, next to the bathroom, kind of the hotel room setup. There's some challenges in terms of ceiling height, structure, ductwork, ventilation that existed there for that to happen. And then also, like early in the project, we didn't know if we could get windows that met the comfort criteria for passive house. And we kind of had to make this decision, like, okay, are we going to need to wash the windows with conditioned air to make up for underperforming windows? That ended up not being the case, but, you know, it wasn't until we got into the exact hinge spec and the force on the handle to like really prove out that we could get windows that worked, which you know, that discussion continued throughout the project. So kind of two point, like we probably couldn't fit the fan coil unit elsewhere on the ceiling or on a wall or anything like that. And then it was just like sort of a sure thing to put it under the window. Now, new building, if you could get the geometry to work out to get it to fit it with the ceiling heights and everything else, that could be an option. But then the ceiling also presents like maintenance concerns and getting in there and it dripping and how do you replace it and everything else. I can also mention, since we looked at VRF as well. And that seemed viable, although, you know, the building was just sort of at the height limit where AKF was comfortable with that. And everyone was concerned about maintenance, about noise, compressors in the rooms, and then also just the ability to track down refrigerant leaks in the future. And folks were concerned, like, something leaks, we're never going to be able to find it. You know, the water-based system, it leaks and you can pretty quickly find it. In addition to like the issues of just having lots of refrigerant in the building, kind of steered us all away from that.
Great, yeah, thank you.
Great, thank you so much. David Levine, you're up next.
Oh, thanks, Amy. Great presentation, again, as everyone said, and a great project. So kudos to the whole FX team. And I know we talked about this, or you talked about this earlier. I don't want to belabor it, but when you coated the interior of the existing terracotta brick, the choice of the drywall product, did you look at a spray-on product or a fabric like an Intello?
I can answer this one. The reason that we were initially going to use just the existing plaster, but when we did a mock-up of one of the rooms, the contractor found that the plaster was just crumbling off where they were having to patch it, or so there was a decision to just kind of encapsulate it with the gyp. So applying a liquid material or a flexible material to that probably would have had the same issue where it would either cause the plaster to peel off, or, you know, in the future it would fall off. We felt like the gyp was a more sure path to go down.
Got it.
Our initial take before those probes was, can we like just skim coat the walls, right? And then, yeah, once you touch that plaster, it will be interesting to see how that plays out during the construction. But once you touch that plaster, large chunks may fall off and just need to be, stabilized on there and have this known surface.
And was it a cost reason that you didn't want to remove the plaster, or was it more about like what you were going to
what you're going to find, cost, time.
Yeah.
I mean, you start removing the plaster. Terracotta also like really likes to fall apart once you touch that. Before you know it, you only have like a face brick of the building left. So
yeah,
try not to touch it if you don't need to, right?
Yep.
Get some unit pricing for change order.
Yeah, right. Yep.
Yes, we did.
Yep.
Great question. Rob Hoskin, are you still here? You're up next.
Yep. Hi. Thanks for the presentation, and I'm sure it's going to be a really influential project. I've just a comment and then a question. Comment is I'm going to be doing a presentation to the Pittsburgh 2030 district next week, and mention this project for sure. The presentation's about envelope commissioning and facade retrofits. So I think, this is a good example to be talking about.
Great.
Yeah, so thanks.
Yeah, spread the word.
Right.
The more this sort of project gets out there as something that's achievable, the more all of you can push this all to the next level and hopefully, bypass this project and doing something even better.
Right. So cities all over the place have buildings like this, and Pittsburgh's a similar climate zone. And my question is about the envelope consultant. Heard about what SGH did a little bit, the WUFI model and the testing in their lab. Is there anything else that they did of interest? And also, is there an envelope testing plan other than blower door testing?
So yes, there'll be an envelope testing plan, specifically centered around the windows. And I mean, they were instrumental in helping us generate and review all those details and specifications, certainly. I'm trying to remember, Jenna, what else? Was there any other sort of testing or analysis that they did? They did multiple versions of that WUFI analysis on different systems.
That's right. Yeah, I mean, they generated the probes and did a lot of reviewing of probes, and then did the blower door test for the 2 units that we mocked up last summer. That obviously isn't a direct correlation to the overall building test, but overall blower door test, but it did help us identify some weak spots.
Yeah, I kind of skimmed over that, but we mocked up the exterior wall assembly during a summer in one of the rooms, did a bathroom renovation as well to understand finishes and test out fixtures and all that other stuff, all as well as we could within the context of not a complete building renovation, and did blower door tests on that room mock-up, which was helpful, but of limited utility since it wasn't the full building and didn't include the actual window and things like that.
That's really interesting, though, that you guys were able to do it on a small scale first, and I'm sure that was informative to the process.
Yeah, that was, that's where we fully appreciated how anything you touch falls apart. So
got it. Great. Thank you for that question. Andrew Peel and Jane Sanders were next, but I think their questions were answered already. So we're going to go to Stephen Tilley. If you're still here, go ahead and unmute.
Okay. Great. Echo everybody else. My question really was about the relative size of in your energy model of the heat loss through the thermal bridge between the slab and the brick. And for example, the sensitivity with adding the triple glazing, it's really about the relative sizes of those of the heat losses in your energy model, and the ways of remedying, which obviously using closed open cell foam rather than mineral wool, and going to triple glazing.
So like what was the penalty for that 14% slab?
Yeah, I mean, it's 14% of the area, but is it, what the question is, what was the component of the total energy loss?
was it like half of the energy lots, or what?
Yeah.
Ooh.
I don't know that. Maybe we have a follow-up that's where we bring on Steven there.
I think my LinkedIn profile was shared at the beginning of this chat, and you should all reach out to me and ask those harder questions, and maybe we can get answers for you. I also found, I think someone asked for the ACEEE paper. I just put that link in the chat.
Great. I mean, it's what we should all be doing and would love to be doing. So thank you so much.
Great. Thank you.
Great. Thank you for that. So we are at 1:15, but we have 2 questions left. If you guys can stick around, Justin Walton is next.
To be careful. The team had ever looked at the product called AeroBarrier, which is able to sort of, through an aerosolized acrylic sealant, help dial in air tightness within existing, also new construction, but especially in existing. Was that ever looked at or considered as a product on this project?
Sounds like a Jenna.
Not. I think we mentioned it in passing, but we didn't. No, we didn't look into it. I mean, extensively, and I'm trying to remember why exactly. It could have been time. Aries, if you have any opinion or answer, feel free. Aries is on from SGH.
Hey, can you hear me?
Yes.
Yep.
Hi, hello everybody. No, this is not something we looked at closely. Also part of the thing that Michael and Jenna were talking about earlier, the initial substrate we were going to use was the crumbling gyp. So we wouldn't feel comfortable installing something on top of that gyp. The product you mentioned, I think, is something that is spray applied. You positively pressurize the interior of a building, and then it sort of finds its way into all the little nooks and crevices and areas where you would have air leakage. But yeah, for our case, it's not something that we looked at.
Given that exterior wall existing condition, we might have needed like tanker trucks full of that to fill.
Yeah, definitely.
Yep, that makes sense. But thank you, Aries, for joining us as well. The last question is from Sasa. If you're still here, go ahead. Maybe I'll just jump in and ask the question. What is the cost comparison to renovation in more traditional or conventional ways? What were the key points to have NYU onboarding the Passive House and LEED certification? So I guess that's a 2-part question.
I've struggled with how to talk about additional costs, and it's like, what's your baseline today, though? For NYU, it's got to be LEED, and it seems, and they're establishing performance requirements of U value of window and air infiltration requirements of 1 air change per hour of 50 pascals as just like, this is what NYU should be doing. So it's like, is that the baseline? And is avoiding local law 97 fines, in 2030 the baseline? If that's the baseline, then this is kind of what you should be doing, right? And
absolutely,
to compare it to Brittany Hall, which, even 10 years ago, we were collectively as a city and institution and architects and industry, we were, even though only 10 years ago, we were kind of in a little different place in terms of energy, right? I mean, we were talking about it, we were doing great projects, but things have progressed so much that I would challenge to say that there's zero cost because this is what you got to be doing. And for many institutions, this is what their sustainability goals are. But again, like LEED was, key, and that DOAS system with its space and cost and everything came up multiple times. And do we need that? And, we tackled that early on, and AKF had written a white paper about their interpretation of mechanical ventilation requirements from LEED and that you needed to do it. So, while that was discussed many times, it could never come off the table.
That's a great answer, Michael. I love that answer to to just say this is what we need to be doing. We're struggling with that on our end as well to be able to give a comparison. It's a question that NYSERDA is asking as well, and it's really hard to quantify.
Yeah, and even like without LEED, okay, like if you're creating this super tight building envelope, and there's 700 showers that are being taken every day, like I think you need some mechanical ventilation in there just from a building design perspective. So
very well said. Very well said. I think that's a really great point to end on. And we thank you again, Michael, and everyone who joined, Jenna and Eris, for your comments. And yeah, we just really appreciate this, and thank you all for joining during the workday.
Yeah, well, thanks for everyone for joining for Passive House Accelerator, and New York Passive House for hosting this. This is really wonderful. Great to have this great conversation, and I'm happy to continue it on LinkedIn or via email or elsewhere. And yeah, thanks everyone.